Steam at 50 bar and 550 degrees Celsius is expanded in a back pressure turbine to 10 bar. If the isentropic efficiency is 70%, determine the temperature of the outlet steam. So there are two ways to solve this kind of problem. First of all, we can simply use steam table, but we need to find a table for the isentropic change of steam condition. So from the steam table, we can identify the enthalpy of the steam in, which is at 50 bar and 550 degrees Celsius. We find out the enthalpy value is this. Then we also check from the table that the entropy at this condition is this value. Okay, then the next step is, because of we know that the system is entropic, so we need to find out what will be the enthalpy. So the system is entropic, so we know that we go to the table and then find out at 10 bar of this enthalpy. So this entropy. So in this case, we know that entropy at point 1 equal to the entropy at point 2, entropy at the inlet equal to entropy at the outlet. And then from the steam table, we will be able to interpolate the value for enthalpy at point 2, which is enthalpy of the point outlet from the isentropic steam table at 10 bar, corresponding to the enthalpy equal to this value. Then by having this value and we know the efficiency of the turbine, we can apply the turbine performance equation here to find out the H3. So the enthalpy, the actual enthalpy of the exiting steam. And then from the table, then we will, so from this calculation, we can get this value. And then we cross-check this value in the table to find out at 10 bar, at the corresponding enthalpy of this value, we get the temperature of the steam is 370 degrees Celsius. Okay, another way to solve this problem is by using the entropy enthalpy chart, like the way we do it in example number 1. So from the chart, so first of all, we need to find out the point where the steam enter the system, which is at 50 bar. You see here this line. This line is corresponding to the 5 megapascal, which is a 50 bar, and we also know the temperature is 550 degrees Celsius. So this is the line for the temperature of 50 degrees Celsius. Basically, the point where the steam entered the turbine is exactly at the point where I put my cursor over there. That is correspond to the enthalpy of this value, which is exactly in between 3500 and 3600. So the value will be 3550 kilojoule per kilogram. Then the exiting condition is 10 bar. Okay, so this is a line of 10 bar corresponding to 1 kilopascal, as you can see over there. Then remember that the cycle is isentropic, so isentropic line is a straight vertical line over there. So from this line, we know that for the 100% efficiency, the condition of the steam exit from the turbine is exactly at the point where I put my cursor here. This point corresponds to the enthalpy of 3050, somewhere there in between. Then from the equation for the turbine, we will be able to find out the actual enthalpy out, H3 here. From the efficiency or given efficiency over here, we can find out the H3. If we look into the chart, the H3 must be somewhere here, so it's crossing here at 70%. So 70% here is basically a ratio between, if you want to look into graphically, so 70% is ratio between, let's say, from this point to this point is, so this is A, and let's say this is B. So A of A plus B equal to 0.7. That's how the efficiency translated into the chart. So the next one, when we know the actual endpoint, we look into this line, and then this line is corresponding to, so you look into the temperature line there, it corresponds to the temperature slightly above 350, and yeah, well, we know it from the previous calculation is about 360 degrees Celsius. Okay, we got this example. A steam turbine shown below required to produce 10 kilowatt of shaft work. Determine the flow rate of the steam required to be expanded in the turbine. So the same as example, previous example, we can use either steam table or we can use the enthalpy entropy chart. So the first solution will be from the steam table. From the condition given here, okay, it's a 550 degrees Celsius and 50 bar, basically the same as the one before. From the steam table we can identify the enthalpy of the steam, and then at a condition number 2, we have this 350 degrees C and 10 bar, and then we can also find the enthalpy of the exiting steam. And then based on the equation here, we know that we have a delta H inlet mean delta H outlet minus delta H outlet, and then from the equation of work we'll be able to identify the mass of the steam, which is equal to this value. Another solution is by using the enthalpy entropy diagram like the one we did before. So we use an exactly step the same as the one we find before. We know that if we compare these two conditions, if we pull the isenthalpic lines, we'll be able to get a delta H equal to 400 kilojoule per kilogram, and then from the data of the power generated by the turbine, we can calculate the mass of the steam resulting in this value. So the key understanding to be able to solve a problem associated with the turbine performance is our understanding in reading the steam table and to use the enthalpy entropy diagram.